This time we'll talk about a very interesting discussion which is dear to my heart, and it's about understanding the Linux kernel preemption models. So you see what happens in Linux kernel is when you build the kernel, if you ever get so excited as to try to build the kernel, you would see that it gives you three different choices in terms of the preemption models. It might say, hey, you want to have no forced preemption, and it says server, that is recommended for the server actually configuration. And for the desktop, it gives you a choice of voluntary kernel preemption, and then it says preemptible kernel, low latency desktop. And usually what happens is that people use, like for example, if you see on this machine, what you see, this is a CentOS server, and you see here when you see uname minus a, it says SMP preempt dynamic. So since preemption is, this is a voluntarily preemptible kernel basically. So if you look at the kernel configuration file that I used for this, you would see that it specifies voluntary kernel preemption as one of the choices. So, or maybe if we go to boot, let's see, if we try to copy the config file from boot and see how, let's say this particular configuration file, even though it is 514 for the 514 kernel. So now you see here, say preempt, let's search for preempt. See here, kernel preempt voluntary. Here you see that, and that's basically, it says that it is voluntarily preemptible kernel. That means if you want in your kernel code, you can keep calling things like might reschedule and might schedule or not, and then it's up to you. Otherwise, it's basically no forced preemption like the desktop. In the sense, if you are in the kernel and you are in a some kind of M delay or something, not M sleep, not like blocking sleep, but basically busy wait sleep, you are basically in a way you're blocking, you're hogging CPU. And if it is a single core system, you're pretty much hogged, you stopped everybody else from running. So we are going to see that using a module and a user space program. So if you see the module, you see that it has things. So we have to load this module. So you say ls mod, and then do a grep for hello. Yes, and it is already loaded though. I already loaded. You know how to load the module using insmod. So here, if you see, hello is already loaded, but what does hello do? Let's see that hello.c. So hello.c, as you can see, is a typical your kernel module. It's very easy, very trivial kernel module. We see them all the time. But what is interesting about it is that in the read system call, it does a m delay on for 5 seconds. It's just busy waits. So this understand the difference between m delay and m sleep. M sleep would do a context switch, but here it's no context switch. You're basically spinning, kind of a spin log, but that is used for a different purpose. This is for like just busy, for no other purpose except to hog the CPU for 5 seconds. So this is what is the only thing that is kind of, I would say, special in the read. Otherwise, there are no other FOPS, file operations structure. Read, write, ioctl, none of them are implemented. I mean, read is implemented, but write, ioctl, and all those are not. That's why your file operations structure is very simple. It just says my read is implemented, as you can see using a. This is the C's. In case you are confused about the new way of initializing a structure in C, they call it designated initializers. So you can actually specify the member name here, saying dot read, by saying dot read. And this is your hello init. This is hello init is your very typical hello init. There are no big deals here. My cdev ops, you have to initialize, honor this module. What is my cdev? My cdev you got using cdev alloc, and my cdev was declared in the very beginning of the function. You see, my dev and my cdev. Now here you see that this thing. So that's your kernel module, and as you see, I already loaded it into the running system using insmod command, in case you're curious. So this is loaded. Now look at the user level program. User mode program consists of two threads. So we have been talking a lot about threads these days, the POSIX threads. So there are two threads here, high prio and low prio. And high prio is, by the way, the threads don't know that they are high prio. See, you say you don't call anything in the thread that says I'm high prio or low prio. That happens outside, like in main. When you create these threads, you set their priority at that time. But in high prio, you can see that I have a sleep for 3 seconds. That's all it does basically. And the low priority thread, what does it do? It basically uh, does it opens this file dev demo, and after opening it reads something from that. And so as you can see, you already saw the kernel module. So when you do the open and the read, in the read it will block for, it will do m delay, busy wait for 5 seconds. So, and then this is how you create threads. And you have pthread type t1 t2 t3, you have attribute type pthread attribute, you have struct scat param, you call attribute init, attribute set scheduling policy, then you set attribute set scheduling parameters. And what is the parameters? The parameters was param.scat priority, and param.scat priority was 50 for the high priority thread here for t1, and for the t2 you can see it is 30. So now let's run this program. I already compiled it. Now you see a dot out. Now what happens? See, so we were expecting 6 seconds, right? But it's only 3 seconds. How come? See, 67, 73 seconds. Something went wrong? No. What happened is that because you have two cores on this box, you see cat proc CPU info, you got two cores on this box. So the other thread gets scheduled on other core, and that means you feel, oh my god, what I was expecting is not happening. So what I should do then? I'm going to do this, run the same program using the task set command. Task set minus C, and then the CPU number 1 dot slash a dot out. And now you see what happens. You have 15, 515, the last three decimal digits, and then you got 521. So it's exactly 6 seconds this time. Why? So what happened is, when you started thread 1, it went to sleep for 3 seconds, and then in between thread 2 started, and it actually got busy in the kernel. And you would say, well, so what, thread 1 can continue to run. But if you've got only one core and you got no force preemption, that means your context switch on thread 2 is not going to happen until thread 2 has gotten out of m delay, so 5 seconds. So that's what is interesting about this program. It tells you about the kernel preemption policy. Now I heard that for voluntary preemption, if you really want to kind of even like assume that we are doing this simulation for one core and we have the 6 second delay, I mean, if you go back to, let's go back to the kernel code. So in the kernel code, you see that user mode.c in the read system call, sorry, no, this is not kernel code, this is the user code. Now kernel code is the kernel module. Here, if you have m delay, and after m delay 5 seconds, if you do, for example, in between, let's say m delay 2, and then you might do a call, like for example might reschedule. There's a call in Linux kernel known as might reschedule, and that might reschedule is a very beautiful call, because what it does is might reschedule. So here if you were to call, like let's say only do 2 second, and then you do a might reschedule, might reschedule, right, this kind of call, and then do a mdelay again. This is for 2 second, busy wait for 2 second, and then you say busy wait for 3 second here. Now here if you have this might reschedule, first try to let's build this thing. So you say make permission denied, okay, lib modules build permission denied. So I guess but basically might reschedule is something you might think of using in these situations in a voluntary preemption case where it's up to you to basically give up the CPU. The kernel will not context switch you out in, as it does in case of low latency desktop, or because you have the no force preemption, you're hogging the CPU. But if you don't want to hog the CPU and you have voluntary preemption enabled, you could do this might rescat call between and then voluntarily give up the CPU. That's what voluntary preemption means. And otherwise you can have, if you involuntary preemption in the kernel code, of course the user code is always preemptible. If you want to do in the kernel code non-voluntary totally preemptible kernel, then you have to use choice number 3 when you build your kernel for low latency desktop. In that case your kernel will be fully preemptible. Now at this point this kernel is voluntary preemptible, meaning if there are more if you want you can have more context switch point by calling this might, like you can say like process may yield, something like that. It's like you're yielding CPU to somebody else, might reschedule, process may yield. If you, so I'm kind of, I'm telling kernel, hey, if you got somebody else waiting, go ahead. But if I don't have this and I have no force preemption, I will be completely hogging the CPU for 5 seconds. So you understood all three. To sum up, you understood all three preemption models in Linux kernel. One is no force preemption. That means your kernel is not preemptible, more or less. And voluntary kernel preemption is like what I just showed you, might rescat. And preemptible kernel is where it doesn't matter if you're doing mdelay, you will be 5 second right here. So even if you, in the case of preemptible kernel, you would have no choice basically, I would say, since it is a busy wait sleep, not a blocking sleep. I wonder if you will get I think what will happen in case of preemptible kernel is, since even if it is a busy wait sleep, you're busy waiting, you'll be context switched out if he sees that higher priority thread is available. That's, otherwise there's no point of a preemptible kernel. Only in case of no forced preemption, you will run to completion, or like busy wait to completion. Otherwise you will be context switched out if it is a fully preemptible kernel, even if it is a busy wait or like whatever. So you understood all three of them. I hope it was a very interesting conceptual discussion today, and not just coding all the time. Those Leetcode guys are like very much focused on algorithms without going into the different kind of concepts. So I thought for a change, let's do some conceptual issues today. So with that, adieu, adios, bye bye.